Hello everyone, my name is Zhiming Cui, coming from Shanghai Tech University and the University of Hong Kong. Now, I will present our IPMI work of hierarchical morphology-guided tooth instance segmentation on CBCT images. Before introducing our work, I will first give some background. Orthodontic is the alignment of abnormal teeth, like the right figure, and many of us has done orthodontic treatments to improve our facial appearance and functional ability, like speaking and chewing. As reported, nearly 50% population have dental problems of various degrees and need orthodontic treatment. In dental clinics, combing CT is one of the most commonly used image modality to make diagnosis and treatment planning. It is a varied type of CT with a cone-shaped X-ray beam and two-dimensional detectors. The advantage of CBCT is the less examination time and patient moment artifacts. Thus, our goal of this work is to make an automatic and accurate tooth instance segmentation from CBCT images. In this way, we should segment all teeth from background tissues and give different labels to different tooth objects. However, automatic and accurate tooth instance segmentation from CBCT is a challenging task. First, the image intensity is highly similar and the contrast is limited, especially at the common boundary between upper and lower teeth in a natural closed-bit condition like the first figure. In addition, the boundary information between tooth root and surrounding bone is also blurred like the second figure. The second challenge is complex abnormalities with irregular tooth positions and directions. As shown in the third figure, the tooths are packing together with grounding, missing, or misalignment problems. Moreover, the tooth root number is different, varying from 1 to 3, especially of molar with multi-roots. As tooth segmentation is very important in dental clinics, many research works has been explored, including traditional-based methods and deep learning-based methods. In traditional-based methods, level set and template fitting are all semi-automatic that need manual input of initialization. Besides, it can't address the closed-bit status with blurred boundary signals. Recently, with the advancement of deep learning, the learning-based methods have attracted much attention. One typical solution is built on mask RCN that use bounding box to represent and guide tooth segmentation. However, these methods usually produce lots of artifacts if another tooth is included in the bounding box. Another stream of methods are anchor-free that utilize center point to represent tooth, which is too sparse to capture the complex geometric information of tooth. To address the above-mentioned problems, we propose a two-stage hierarchical morphology-guided tooth instance segmentation network. In stage 1, with the input 3D CBCT image, we first automatically extract the tooth central point and skeleton lines. The central point is a stable signal to detect and distinguish different teeth, and the tooth skeleton is an efficient signal to represent the tooth structure. With the output of the first stage, we design a multitask learning to segment individual teeth and simultaneously predict the landmark defined at the tooth root apex and the corresponding boundary, which aims to extract more useful features of tooth segmentation task. Now, let me introduce the details of our network. In stage 1, with the input of 3D CBCT image, we first design a central network to output the centroid offset and the binary map. The centroid offset is the vector of each tooth's voxel point to the corresponding central point, which is a 3D vector in x, y, z directions. The binary map indicates whether the voxel is belonging to the tooth or not. Similar, another subnetwork, tooth scattering network, is also proposed to extract the 3D scattering offsets and binary map. With this information, we first detect the tooth objects based on the centroid offset. In the first step, we use common boundary binary mask produced by the centroid and scattering network to mask the centroid offset map. Then, the predicted 3D vector is added on the corresponding 3D coordinate to obtain the centroid voting map. For example, if the voxel is pointing to by n times of the offset map, the intensity value is n. At last, we employ a fast clustering method to detect peaks on centroid voting map and set it as the different tooth objects. After detecting each tooth from CBCT image, the voxel-wise index information is then mapped to the scattering offsets and obtains the tooth scattering of each tooth. At this stage, each tooth is successfully detected and represented by scattering to cover the complex structure. With the output of the first stage, we propose a multitask learning to segment each tooth object guided by its scattering. Specifically, we first select one tooth object and crop the image patches from the original image and the tooth scattering map, respectively. Then, with a shared encoder, 3 task-specific decoders are used to predict the tooth mask, root landmarks, and boundaries simultaneously. These 3 tasks are related from a geometric perspective and can intuitively boost segmentation performance. After each tooth being segmented, the final result can be obtained as shown in the figure. To evaluate the performance of a method, we collected 100 data from dental clinics, and 50 scans are used for training, 10 scans for validation, and the rest 40 scans for testing. The metrics including the tooth segmentation task of dice score, average surface distance, and host of distance. In addition, we also calculate the detection accuracy about the percentage of successfully detected teeth. To validate the effectiveness of each component, we set up the 4 configurations. BNet means it utilizes tooth centroids to detect and represent tooth in the first stage, and a single task network in second stage for tooth segmentation. BNet-S means it adds scattering in stage 1 to better represent each tooth. It can be seen that with the tooth scattering representation, the 4 metrics are consistently improved. Also, from the visual comparison, it can be found that the molar with multi-roots can be separated more accurately. Then, in the third version, we add a tooth root detection task in stage 2. From table 2, the host of distance with tooth root detection is significantly improved due to the segmentation accuracy at tooth apex points usually divides the maximum distance between prediction and ground truth. The visual results also demonstrate that with the help of tooth root landmark detection task, the segmentation at the roots can be improved. To validate the effectiveness of the final component, tooth boundary prediction in the second stage, we add it in our full net. It can be seen that the full net achieves the best performance And as shown in the figure, even in the in-sensor tools with mental artifacts, our method can still segment accurately. In addition, we also compare our method with other 3 algorithms that achieves the state-of-the-art performance. The first is the MWT-net that utilizes tooth boundaries to separate and segment teeth. The second is the ToothNet, which is built on mask RCN that utilizes bounding box to group and segment tooth. The last is the CGD-net, which uses tooth center point to guide tooth incident segmentation. As shown in Table 2, our method obtains the leading performance at both segmentation and detection metrics. To further demonstrate the advantage of our method, we also provide a visual comparison of 2 typical samples. It can be seen that our methods match better with ground truth, especially near the tooth apex and the occlusion plane with blurred boundary signals. Notably, MWT-net is more likely to lead to failure in tooth separation. Moreover, ToothNet and CGD-net respectively represent each tooth by bounding box and center points, which will produce lots of artifacts near the tooth boundary. At last, let me conclude the contribution of our work. First, we propose a novel solution for automatic and accurate tooth incident segmentation, which achieves the best performance. The most important is our design of a hierarchical morphology-guided network, which represents and segments tools from points to line to surface. It is a genuine method and can be directly used in other tasks of organ segmentation. Thanks all.